Before we start, I just want to go through this page, page 142 on your manual, talking about different values being low or high based on these conditions. I think they're all the same. So just to keep all this in mind, with severe anemia, which is low hematocrit, low hemoglobin, right? So note on page 141, the normal hemoglobin values in grams per deciliter. Males 12 to 17 and females 11 to 16. So 15 is right in the middle and 10 would be low, just to give you an idea, perspective, what anemia looks like. So the partial pressure of oxygen, of course, with anemia is going to be normal because that would be a ventilatory problem. The SaO2, now this is arterial blood gas, is within normal limits. The gas is normal. And if you get a pulse oximeter, it's going to be normal as well. But the main value is the CaO2, which we did the calculations. We'll do that again. So the CaO2 is the absolute amount of arterial oxygen in milliliters of oxygen per deciliter of blood. So all of these are going to be low. CO poisoning, VQ imbalance, and elevation altitude. So with carbon monoxide poisoning, you're going to have low oxygen binding because, as I mentioned before, hemoglobin has a higher affinity for carbon monoxide. So it's going to choke those binding sites on hemoglobin. So the PO2 in the blood, you still have the oxygen getting there unless you have a problem with ventilation. The PaO2 or PO2 is going to be normal. But the saturation, of course, drops. And if that happens, you're going to have a decreased CaO2, the absolute amount of oxygen per deciliter of blood. Any problem with the VQ imbalance, of course, you're going to have low partial pressure of oxygen. So whether you have a problem with ventilation, pulmonary ventilation, or perfusion, which perfusion is done during external respiration. Remember, external respiration is the same as alveolar respiration. And then you have perfusion to the tissue, which is tissue respiration, also known as internal respiration. So all those values are going to be low with a high or low, but especially low VQ imbalance. High altitude, the problem is the partial pressure of oxygen. That's why when you're at higher altitudes, or we're at sea level, the higher you go above sea level, the partial pressure of oxygen drops in the atmosphere. So that's obviously going to be low in the blood. And that will decrease your SaO2. And if your SaO2 is low, you're going to have a decrease in your absolute, which is the CaO2. So that's really important. We'll start at the beginning. Slideshow if we can. So pulse oximetry, and this is the pulse oximeter, which we showed you before. And if you come into the lab anytime, it's very easy. You know, it just takes a couple of seconds to get it started, in a minute or two to get it working. You'll see the oscillatory pulsations. You'll get the hemoglobin saturation of oxygen in percent. Remember, the normal hemoglobin saturation with oxygen should be between 95 and 100. It should be over 95. Because if it's at 90, that should be a time when you're in the ICU. That's an ICU point. Arterial, remember this is all arterial. If it goes as low as 75, you're probably looking at cyanosis. You can also see the pulse waves, the strength of the pulse waves. You won't measure them. The machine will give you the readout of the pulse. And I mentioned before the difference between peripheral pulse, which is really what SpO2 means. SpO2 is the actual pulse oximeter, like you put on your finger, and that's a peripheral pulse. It's away from the heart. So apical pulse is closer to the left ventricle, right? The fifth or sixth intercostal space, mid-axillary or anterior axillary, and you can take a pulse that way by leaning into that. area, and you check pulses with your fingers, not your thumb, because that has a pulse. So SpO2, when you see SP, that's the pulse oximeter, because this is a peripheral pulse, not done by a blood gas, an arterial blood gas, which is different. So another difference between, apical pulse and peripheral pulse, it really is just location, but the heart rate should be the same, and the pulse waves should be very similar. Of course, you could have bigger pulse waves in apical and the carotid than you will maybe on the dorsalis pedis, which are peripheral pulses. Okay, so again, we're going to use the machine on an index finger, or use the finger probe, and we'll talk about that. So this is the reason why you may not have good pulsations in a peripheral area like your finger, like hypoperfusion. That's decreased blood flow into that tissue that's peripheral. It doesn't necessarily mean you're in shock or you have blockage or occlusion. It could mean just some sympathetic vasoconstriction. But really what the sympathetic nervous system does is redirects your blood flow away from the periphery. And that's why you get frostbite when you're cold. So these kind of go together. Hypothermia would cause peripheral pulses to decrease. And of course, heart failure, getting the pulsatile blood flow to the periphery could be a problem if you're in cardiogenic shock, or hypovolemic shock, where you're actually losing blood. But these are going to decrease the pulsations that are going to be even have a chance to be absorbed by the pulse oximeter. Of course, broken bone, if there's no blood flow, that's a problem with tissue perfusion, right? Or tissue respiration. Sometimes you take the pulse oximeter too tight, which could cause both. They can cause decreased perfusion to the periphery, or it could cause too much venous engorgement, which is the next page, right? So know that when you do your book, all the answers are here, so to help you understand, how to answer those questions and none of this is on the exam on Friday, right? This is going to go, because you're missing a Friday. We're not going to have a lab for 3 weeks, technically. So that's why I wanted to get this done today. So these are too many pulsations. Sometimes you have engorgement, right, of the veins, and that could cause excess pulsations. Movement, like remember artifact with the EKG? Everybody kind of knew what that was when we move skeletal muscle. So movement of the finger is going to increase your pulsations and give you a false high reading, pulse-wise. And it may look erratic too when you're looking at the pulse oximeter. So shivering and cold, of course, that's going to cause both problems. And then, if you're monitoring and somebody has a seizure during this time, whether it's a short clonic seizure or an ongoing myoclonic seizure that goes for a longer period of time, you can see a change because of the contractions. Same thing with a Parkinsonian tremor, which can cause what really looks like an artifact. So the pulsations are really important, and these waves, the top of these waves are your systole. And remember this, I know I said this a lot before, but what the pulse oximeter is testing, what the arterial blood gas is testing, like it says, is arterial blood. It's never dealing with venous blood. Because the venous blood, the veins don't have this kind of pressure, first of all, the systolic pressure and the walls that the arteries do. That's why we studied all the histology of the arteries and the left ventricle. So this is more problems with excess venous pulsation. And this is the one you should know, right-sided heart failure. Like if you have a problem with the right side of your heart, you have backflow, let's say you have an insufficient tricuspid valve or pulmonary valve, where's the backflow going to be? Into the systemic veins. So that could lead to the periphery. And you can have excess pulsations because of that excess backflow of blood or stasis of blood. So the veins start to pump a little bit. They have tunica medius too. And that will give you a false reading as it adds to the arterial pulses. So basically the oximeter is looking at the pulses through the pulses when it's at its highest. And you should have at least 5 pulsations on the pulse oximeter to get a reading. So it takes a couple of seconds. Whether you're using the machine here with the oscillator or when you get a Walgreens or Rite Aid. So all of this would cause venous engorgement. Like taping it too tight also caused less pulsations, right? So it can really cause both, if you notice that. And this, I heard you did this in lecture. So the hemoglobin oxygen dissociation curve, where oxygen is either bound to hemoglobin with a high affinity, like up in this plateau region, or the steeper region where hemoglobin tends to dissociate the oxygen, the oxygen is removed from the hemoglobin. And of course, this happens at different areas. So at 100 partial pressure of oxygen, which is right after the blood is coming out of the lungs, right? You're going to have a very high saturation. So saturation is a percent. Partial pressure of oxygen in the blood now, this is in the blood, not the atmosphere, is in millimeters of mercury. So when we do our CaO2 calculations, the saturation of oxygen on hemoglobin is going to be a decimal. Unless it's 100, then it's 1. And the partial pressure of oxygen on the solubility side of the equation is going to be a whole number, because it's millimeters of mercury. Because the lovely Professor Liberty, she made a little mistake on that. Like when I think the numbers are slightly different. So I did them before, and I'll do them again so we have the right numbers. Because it might make a difference. I'm not going to trick you by using her numbers and testing you. I'm just going to make sure you're in the right ballpark, right? So if you heard me before, the whole idea of this pulse oximetry is taking the total amount of hemoglobin and finding out how much of that hemoglobin is oxyhemoglobin. Remember, I showed you before, oxyhemoglobin is hemoglobin bound with oxygen. Free hemoglobin, which is blue here, is reduced hemoglobin or deoxyhemoglobin. But there's never completely deoxygenated hemoglobin. It's always at least 40%, right? Under normal circumstances, right? Under normal circumstances. So the typical, and that's why I like this down here, and the next picture is even better. It shows you where we are. We're in the arteries at this saturation, and we get down into the veins at like that 70 or 75 in the veins, systemic veins. And then you get into the working cells where the oxygen is just dumped off. There's more carbon dioxide in that blood. So if you have 16 molecules of hemoglobin total in that deciliter of blood, and half of them are oxyhemoglobin in the arteries, though, in the arteries. That's a really bad number, right? That's way below ICU point, and it's below cyanosis. Big problem. 75 is great for the systemic veins, but horrible for the arteries because then we'll be in cyanosis at that point. 100% is great, what we're looking at. So far, the only one I saw was Nicole. She was the only 100%. Okay. Same thing, just the affinity for oxygen on hemoglobin. Hemoglobin's affinity, loving the oxygen, is highest at the higher partial pressures of oxygen. So it makes sense, as you're going to the tissue, the hemoglobin affinity is going to decrease. And what happens is the Bohr effect, where oxygen is dissociated from the hemoglobin to go into the tissue, into the cells, go into the mitochondria and make ATP, right? Make more ATP for our potential energy for our cellular cycle energy. So it depends where you are. But remember, we're talking about arterial blood in this range. By the time it gets to the veins, the venous veins, or the venous system, then the oxygen is dumped off, but it's still 75%. So I mentioned before, hemoglobin has 4 binding sites for oxygen. So when all 4 are bound, that's 100%. When 3 out of the 4 are bound, that's 75%. So it's never without oxygen, unless there's a pathology. Yeah.
So the steeper region is venous blood, right?
Yeah, very good. It is. Makes sense. Like when you think about that, when you do your O2 sat. Now, I'm not going to ask you about it going to the right or left. If it goes to the right, which makes the saturation a little bit lower, that means that oxygen is more likely to be dissociated off of hemoglobin if this curve goes to the right. So you could remember like high carbon dioxide levels, which is called hypercapnia, will cause this curve to go to the right. So you'll dissociate more oxygen off of the hemoglobin, the affinity goes down. If your temperature, body temperature goes up, that would make this curve go to the right to dissociate more oxygen off the hemoglobin. If your blood is acidic, less than 7.4 pH, this will go to the right. So pretty much when you're sick, right? When you're sick, everything goes to the right. So your oxygen binding capacity goes down a little bit when your hemoglobin has less affinity. The only reason it goes to the left is the opposite of what I just told you. So you have very low carbon dioxide or alkaline blood or hypothermia or you're a fetus. Then this curve will go to the left. Okay, so really I'm interested in this, knowing the relationship in the blood of the partial pressure in millimeters of mercury of oxygen. And when we do acid base, we'll do the partial pressure of carbon dioxide. But for this lab, it really isn't, it's not that important right now. And then what happens in the systemic blood, like Pusher said, when you have systemic veins, now you have less affinity in the steep region for oxygen on hemoglobin, and the hemoglobin dissociates the oxygen. Completely appropriate here at 75% saturation, which could be as low as 40 partial pressure, but that's in the veins. Well, this pulse oximetry is all about the arteries. You have to remember that. And in the working cells, of course, you could have an oxygen saturation between 30 and 40, which is very low, but completely appropriate in that area. There's more carbon dioxide than there is oxygen. Because ultimately in respiratory, you're going to learn that that's how we get the carbon dioxide out of our body through the Haldane effect, which is going back to the lungs and exhaled or transported or diffused through external respiration, which is also known as alveolar respiration. This one is good because it shows you the actual comparison. And it's directly proportional, as you can see. And PaO2 is the same as PO2. It's the same thing. There's no difference, right? So at 100, you're going to have very high saturation. Makes sense. At least 98%. So where's the problem? When we get around 70 and it goes below 95. So 80 is acceptable partial pressure of oxygen in the blood, right? Because you're still going to have a directly proportional 95% saturation. But when you get here to 60, this is what you have to remember, that when you get to a partial pressure of 60 in the blood of oxygen, you're going to have an SaO2 of 90, which is not acceptable. That's the ICU point. And if it goes below that, you're in bigger trouble, heading towards 75% saturation, which is your cyanosis, most likely cyanosis. So this is showing you somebody with cyanosis. Blue nail beds, blue lips, blue around the sclera maybe. But again, like I mentioned before we used pulse oximetry, you'd wait for this before you gave supplemental oxygen or realized that the patient was in respiratory distress. So now at least you can monitor with the finger pulse oximetry with SpO2, right? You don't have to draw any blood, you put it on, you can monitor, see changes. Like in lab, and you can do this if you have time today. You can come back if you want. Just do the exercises that we could have done in lab, which is just like walk in place, hold your breath, things like that. Just to see, from moment to moment, how you can measure that on the pulse oximeter, the SpO2, which is peripheral saturation of oxygen and peripheral pulse. And you can note pulse changes, and you can compare this all to an EKG with the changes in heart rate, your tachycardia, bradycardia, stress, exercise stress, along with doing blood pressure. And I mentioned before, of course, when you're doing pulse ox, finger pulse ox, SpO2, you never do it on the same side as you're taking blood pressure because you're occluding the blood flow to the peripheral tissue, right? And also the nail polish could make a change. If it's a darker acrylic nail polish, it could change the absorption of the infrared light or red light. So usually, and also the lights from the ceiling could change the pulse oximeter absorption. So you put a washcloth on top. Sometimes that'll help to block the light to make sure all of these are normal. So this is important. SO2, like I mentioned before, is basically when we already agreed on these two, or which one we're going to use. Like SpO2 is peripheral pulse oximeter. SaO2 is always the arterial blood gas. So that's what we do when we take the arterial blood. Remember, this is not in a vein. This is arterial blood being drawn and then put into the oximeter or co-oximeter, whatever this is, whatever she's trying to find out. Right? So this is an arterial blood gas. And that'll also give you the carbon dioxide levels. It'll give you the levels of carbon monoxide or carboxyhemoglobin or methemoglobin or sulfhemoglobin and free hemoglobin as well, and oxyhemoglobin, of course. So that's really the only difference. The SP is talking about the pulse oximeter, peripheral. SA is arterial blood gas. SO2 is really both. But by the time we're using this, we already decided there's no anemia or there's no other change, and we're comfortable with the number. So again, if there's nail polish, it's going to change the outcome of the pulse oximetry. So we want good pulsatile waves because that's what's being measured, the hemoglobin in that sample, peripheral. Pulse oximeter, SpO2, right? That's not arterial blood gas. That's pulse oximetry. So as I mentioned before, it's the percent of oxyhemoglobin of the total hemoglobin. It's not the ratio between oxyhemoglobin and deoxyhemoglobin. It's the ratio of oxyhemoglobin to the total amount of hemoglobin, right? That's really important. Because I know we did, like for our exam, you have to calculate FEV1, FVC ratio. So that was, normal. This is total amount of hemoglobin. And that's divided into the oxyhemoglobin. And the machine does that for you. You're not going to have to do that calculation. Calculation you need to do for this lab is the CaO2. So that's really important. At the end, you get the right numbers. And make sure you see what's on the PowerPoint. And again, if you listen to the PowerPoint, be careful. It's very long, but she does make a mistake in the second PowerPoint. And you'll see it. You'll see it when you're going through, and I'll show you here. So what do we see is the actual wavelengths are being absorbed in the arteries. So the two wavelengths we're going to use are infrared, which is about 920 nanometers. So that 920 nanometers, that wavelength of infrared, is going to be absorbed by oxyhemoglobin. So that's the good one, right? That's the one we want. Red light, again in the electromagnetic spectrum, visible light, red light is about 660 nanometers, and that's what free hemoglobin is going to absorb at, right? So this is the pulse oximeter. So remember, when you use the pulse oximeter, you put that probe on your finger, the light should always go from top to bottom. The sensor is on the bottom because it's going to have the absorption. So the sensor is on top, your finger goes in here, and then the light is distributed in it only uses two different wavelengths for a pulse oximeter. Later on, you'll see the co-oximeter could do much more and see different types of hemoglobin, but this only has two. 660, which is red nanometers, 920, which is infrared. Infrared is going to be absorbed by oxyhemoglobin, where red is going to be absorbed by free hemoglobin or reduced hemoglobin. It's the same thing. So the sensor is on the bottom. So if less photons reach the bottom, or the LED, light emitting diodes, reach the sensor, that means it's being absorbed. It's not getting to the sensor. And that's how it calculates it, basically. Okay, so again, this is showing just how much. I'm not going to put these on. Just note, and this is a little different. Of course, the nanometers are slightly different, but we're going with the 920 and 660. So it shows how much is being absorbed from both. Total hemoglobin is both. So it depends on the concentration within that blood of oxyhemoglobin, whether you're going to get more 660, which is a problem, less 920, depends on which one it is. So this is good. It shows the infrared light is being absorbed. It shows how much. So it's a concentration. This is kind of a good picture because it shows less. So it shows more of that diode going to the sensor, where with the more oxyhemoglobin, less is reaching the sensor, right? So that's how it's done. So this again is, if you mix these both, you can see that there's more infrared light being absorbed in the finger. So this is good. So this, we're not doing this calculation, but you can see that there's more oxyhemoglobin than there is deoxyhemoglobin, also known as free hemoglobin or reduced hemoglobin. Any questions there? Again, it's a long narration, but it's worth listening to. If you can, it goes through each one of these very slowly and helps you understand, I think. Okay, so it's the same thing though. It's the amount of hemoglobin you have and the amount of oxyhemoglobin in that total hemoglobin. And that's all the SpO2 is. That's all the pulse oximeter is showing you. It's not telling you how much hemoglobin is in there if you're anemic, right? It's not telling you the absolute amount, like CaO2, which is going to take into account the total hemoglobin. It's going to take into account the saturation of oxygen on hemoglobin. It's going to take into account the solubility of oxygen in the plasma and also the partial pressure of oxygen in the blood. So again, more of the same, just showing you 50, 75, 100% and how it would look. Like this would be 50%. If both of these were added together, total hemoglobin, it's 50-50, right? Which you don't want in arterial blood. This is a little bit better. Maybe this is 80%. Is that good enough? No. Not in the arteries, it's not, right? It's got to be at least 95, or else you're going to be in respiratory distress. So you can see this is 50%. This is less than 50%, and this is greater than 50%. If you want to use that as a guide, just to show how much is being absorbed on that sensor on the bottom of the finger. SpO2. Right? So now we're starting to get there where you really have to take other things into account, and the pulse oximeter doesn't do that. So I mentioned before the downfalls to the pulse oximeter versus the arterial blood gas is that it doesn't take anemia into account. So you could have 100% oxygenation saturation of hemoglobin, but still be in respiratory distress because you're anemic. Your hemoglobin levels are low, maybe because your blood cells are low, red blood cells are low, or your iron is low. So this curve adds a little parameter here on normal hemoglobin, which is 15 grams per deciliter of hemoglobin versus 10, which is low, right? Because what's the normal hemoglobin? It's on page 141. So 15 is right in the middle. Male is 12 to 17, female is 11 to 16. So 15 is always in the normal range, 10 is always low. So they use that a lot. So basically what it's showing you is the CaO2, which we didn't calculate yet, and how much actual oxygen carrying capacity you have based on the hemoglobin now. So you have to do an arterial blood gas for that, or a CBC at least, to get the hematocrit, to know how much hemoglobin you have, how many red blood cells you have, how much iron do you have. The pulse oximeter doesn't tell you that. Also, if you heard me before, things like carbon monoxide, which can bind to hemoglobin, hemoglobin has even a higher affinity by 20 times for carbon monoxide than it does for oxygen. So the carbon monoxide poisoning or exposure to carbon monoxide, like smoking cigarettes, generator fumes, exhaust from a furnace or a car, the carbon monoxide could actually bind to your hemoglobin and block oxygen binding and cause respiratory distress, of course. But the problem is carbon monoxide or carboxy hemoglobin gives you the same readout on the SpO2 on the pulse oximeter because they absorb at the same wavelength. So that's a real dangerous thing, which I'll show you. So get the terms down. This could be an H attached there, like free hemoglobin or reduced hemoglobin. Reduced is when you give up an electron, right? You give up an electron. So hemoglobin is actually a buffer in the blood. You see, buffer is the hydrogen. That's why they call it reduced. And same as free or deoxy hemoglobin. This is the most important one, oxyhemoglobin. Good. Carbaminohemoglobin is normal because carbon dioxide, 23% of your carbon dioxide in your blood is carried on hemoglobin, but not on the heme part, not on the iron bound part of the iron binding site. It's bound to the globin, which is the protein, the polypeptide chains that are part of hemoglobin. So carbon dioxide bound hemoglobin is called carbaminohemoglobin. So oxyhemoglobin, now the red blood cell I mentioned before each red blood cell has about 250 million molecules of hemoglobin. Each can carry 4 molecules of oxygen. So the red blood cell is 97% or more of the oxygen in your body is carried on the red blood cell to the tissue, right? So the rest is dissolved in plasma. So less than 3% of oxygen is dissolved in plasma. Whereas carbon dioxide, 70% of the carbon dioxide in your blood is carried on the bicarbonate ion, making carbonic acid. 23% is bound to hemoglobin through carbaminohemoglobin. 7% is dissolved in the plasma. So carbon dioxide has a higher solubility coefficient than oxygen does in the plasma, which is mostly water. Right? These are lipid soluble substances, these gases, oxygen and carbon dioxide. Now, carboxyhemoglobin is the carbon monoxide one. Methemoglobin is that reduced iron containing heme, which changes the binding, changes the color. And sulfhemoglobin, same thing. So the problem is these 3 hemoglobins, which in excess are, of course, are pathological, can block oxygen binding, excuse me, they all absorb on the pulse oximeter about 920, which is infrared. So somebody in respiratory distress, carbon monoxide poisoning, or methemoglobinemia, sulfhemoglobinemia, excuse me, will be in respiratory distress. So you have to take into account that, and this is one of the drawbacks of the pulse oximeter. So somebody could smoke, and within 4 hours, their O2 sat on a pulse oximeter could be 100%. But it's a false reading because carbon monoxide from the cigarette smoke. So this is an example of what happens to the iron. It's further reduced to iron 3, and that changes the color. It changes the oxygen carrying capacity, right? And this is this. She doesn't look, again, I noticed this before, she doesn't look like she's in respiratory distress, but she most likely is, right? Because you're decreasing the oxygen carrying capacity, which changes the color of the hemoglobin and the red blood cell in the blood. That's why you get that bluish complexion with methemoglobinemia. Carbon monoxide poisoning, like we're talking about, hemoglobin has a higher affinity for that. So again, this could choke the hemoglobin, so you can't bind oxygen, and you're going to be in respiratory distress. Of course, this can be very, very bad, right? Because hemoglobin has a higher affinity for carbon monoxide, and that's called carboxyhemoglobin. When it's bound, hemoglobin is bound to carbon monoxide. But the problem is they all of those carboxyhemoglobin, methemoglobin, they all absorb around the same wavelength as oxyhemoglobin. So that's going to give you a false high reading. So this is why it's important to do what's called a co-oximeter, which again requires an arterial blood gas to have this done. So you know exactly what the false reading is about. You know the person is in respiratory distress. They may have pulmonary function tests that are a problem. They may be cyanotic, gasping for breath, and without pneumonia or without emphysema. So carbon monoxide or carboxyhemoglobin absorbs around the same wavelength at 920 that oxyhemoglobin absorbs that. So the co-oximeter will tell the different absorptions. Again, you need an arterial blood gas for these because these three, carboxyhemoglobin, methemoglobin, and sulfhemoglobin, will all absorb around the same time, or the same wavelength. I'm not going to talk a lot about that on the exam. You just have to know carbon monoxide is a big one to know, and why it's false reading, and why the pulse oximeter is not good enough if you're trying to rule out carbon monoxide poisoning. Because it could look like the saturation is normal. So this is talking about, again, we're ultimately going to this CaO2. CaO2 is the absolute content of oxygen in milliliters per deciliter of blood. And basically that's what these numbers are representing. But you should be able to calculate it. I guess I on page 140 something, but I'll do it right off the PowerPoint because the same problems I believe are here. So here's the thing. This is the top picture here. I don't know if you can see my arrow, is normal blood smear. Okay, within say a deciliter of blood on that slide. So the CaO2 with a normal hemoglobin of 15 grams per deciliter, the CaO2 comes out to be 20.4 milliliters per deciliter of blood. So you have to remember, first of all, the units of CaO2 is milliliters per deciliter of blood. And the normal range is 16 to 22. So again, the normal range of CaO2, the absolute content of oxygen, and it has to be done with the arterial blood gas, is the normal range is 16 to 22 milliliters of oxygen per deciliter of blood. So the middle picture is anemia with low iron or low hemoglobin, low red blood cells. So 10 grams of hemoglobin per deciliter of blood. And you see you have a relatively low CaO2 of 13.7. So that's much lower oxygen carrying capacity in that blood. And it makes a big difference. Going from 20 to 13 is a huge change. And when you consider how many red blood cells we have and how many 250 million molecules of hemoglobin per one red blood cell, 5 liters of blood. So it's a huge dip. Polycythemia, we mentioned before, which is when erythropoietin is released, usually when you're having emphysema, you're at a high altitude where the partial pressure of oxygen drops. And your kidneys will send the EPO, the erythropoietin, to manufacture more red blood cells in the red bone marrow. So the hemoglobin can go up to 30 grams per liter. It doesn't make the oxygen carrying capacity any better initially. It takes time for that to develop. And it depends if you lived above sea level for a long time. So you're going to feel sick if you go above sea level very quickly. If you try to climb a mountain that's 1,000 feet, 2,000 feet, 10,000 feet, it's going to change as you go up slowly. It takes weeks, right, for someone to even climb Mount Everest or something like that. The Sherpas who live there, they live there forever. Their generations have been there forever. So they could adapt to this polycythemia and their oxygen carrying capacity works out. So we're going to, from our exam, we're going to talk more about the difference between normal and anemia. And then, of course, the changes in all the other parameters. So here's how we calculate CaO2. There's two parts to the equation. The left side of the equation is about how much oxygen is being carried on the hemoglobin. So you have to get the hemoglobin number for that, hopefully around 15 or so. And then you multiply a number that you have to memorize, which is 1.34 milliliters of oxygen per gram of hemoglobin. That's how much oxygen 1 gram of hemoglobin can carry in milliliters, right? The volume of that gas, 1.34. And then you multiply by a decimal, which is the SaO2. Unless it's 100%, then it's just 1. Right, so if the SaO2, the saturation of hemoglobin of oxygen, is 95%, you'd have to multiply by 0.95. That's a decimal. The other side of the equation uses a whole number, the PaO2, which is millimeters of mercury, partial pressure of oxygen. It could be PO2, it's the same thing. And then you multiply that solubility coefficient. So here's another number you have to memorize. The 0.003 milliliters of oxygen per deciliter of blood. And that's how much oxygen can be dissolved in the plasma in an otherwise normal person. Okay, so that's the equation. Again, anybody have a calculator handy? We could do one of these and I'll do it for you so you have it on recording. Again, CaO2, the units, really important. Milliliters of oxygen per deciliter of blood. Please remember that. Okay, a couple of things you have to memorize. On the left side of the equation, that 1.34 milliliters of oxygen per gram of hemoglobin. You'll be given the hemoglobin number, and then you'll be given the SaO2, which is put in as a percent, a decimal, unless it's 1. The other side of the equation is the partial pressure of oxygen, which is a whole number, millimeters of mercury, right? And then times the solubility coefficient, which is 0.003 milliliters of oxygen per deciliter of blood. And you add those two together, left and right side of the equation, and you get the CaO2, the absolute content of oxygen, and the units are milliliters of oxygen per deciliter of blood. Because you can't take all of the blood, the 5 liters, we just take a deciliter sample in the arterial blood gas. So this is a little further than the actual SpO2, which is the pulse oximeter. So anybody have a calculator ready, please? Everybody good? Let's see where we are. So we're going to look at patient A. Patient A, let's get the hemoglobin first because we're going to get the CaO2 of patient A. So you're going to get the hemoglobin, which is 7, times the milliliters of hemoglobin per, of oxygen per gram, which is 1.34, right? And you're going to multiply that by the saturation, which is 0.95, correct? And then you're going to add, on the other side, you're going to add the solubility of the oxygen. But you have to multiply the coefficient by the PaO2, which in this case is a whole number, 85, times your 0.003. And you add those two together. Anybody have that number? The final number? So this is like 8.9 around there. 1.1. I did this for you because again, the recording, not the recording, the narration is wrong. Because I think she either should use the decimal here or use a whole number here. So make sure this is a decimal. Or if it's 1, it's 1. 100, it's 1. And this is a whole number for the PaO2. So the other side of the equation was about 0.255. Does that sound about right, Maria? And if you add those two together, what do you get? Yeah, so 9.2 milliliters, of O2 per deciliter of blood. Now, does that fall into the range for normal CaO2? It does not, because what's the normal range? I think it's page 141, is 16 to 22. So this is low. This is low. And really why? Most likely this is anemia.
You said 15 was the average, right?
15 is like a good number that we use for like normal men and males and females. Yeah.
Okay.
Yeah. So if you see 10 or below, that's going to be low. Yeah. So patient B, let's do the CaO2 there. For patient B, this was A, now B. So what's the hemoglobin now? That's 15, which sounds normal, right? That's normal. 15 times your amount of oxygen that's carried in 1 gram of hemoglobin times your O2 sat, which in this case is a little bit lower, right? 0.85, and that's always a decimal. And then you're going to add the other side of the equation. Now we need the PO2, which looks low. But let's see if this person may be okay. You don't know. And you multiply that by the solubility coefficient dissolved in the plasma of oxygen. And what do you get there? Let's see if I did this right. So the total is 17.3. Yeah, I got the same. That's correct. 17.3. So this one was low. 17.3 milliliters of oxygen per deciliter of blood. And if the CaO2 range is 16 to 22, this is within normal limits. WNL is within normal limits. Okay? So at least they're getting enough oxygen to make ATP, to get into their cells and function, right? Even at that low SaO2. So obviously this is a person who has a respiratory condition, a ventilatory condition. So do they need oxygen supplemental? Depends on that CaO2. So using